Alrighty guys, so we are going to do 2 lessons today just because they go together. I keep them separate as lesson 2 and 3, but technically we're using lesson 2 to do lesson 3, so we will do both, but we'll do lesson 2, then I'll let you work a little bit, and then I'll quickly do lesson 3 with you. So our power rule is probably the rule that's used the most. Okay, so let's go through first of all and just do the constant rule first. So if we have a function, okay, so I'm just going to break what this is actually saying. So f is a constant function, so if f of x equals c, then the derivative of f of x is 0. Does that make sense? Does that all make sense to you? Because again, look at an example. So this would be an example. F of x equals 4. If I take the derivative, what's the derivative or the slope of y equals 4? 0, right? Because y equals 4 is a horizontal line, right? Our derivative function is our slope function. So the derivative of a constant is always going to be 0. So that's what this first one is saying, okay? Now our power rule, okay, is if you have f of x equals x to the power n, so you have a term, okay, to an exponent. How you can get your slope function in one quick, easy step, right? Look at this pattern. I'm just going to highlight it so you know what I'm looking at. Yeah. Right, so if we have a function x to the power of x, our power rule states that the derivative function is the exponent can come out into the, where, what part? What is that pattern saying you guys should be able to do? Right, to the front, okay? So your exponent can come down into the front, and then what happens to your exponent? You subtract it by 1, okay? So this is one quick, easy step to be able to find your slope function. So what I'm saying is this is going to be this easy. If you have f of x equals 3x squared, do you guys agree that you could use your limit equations to get your derivative, right? Or your limit as x approaches a? So you could do that. You have the ability to do that. I'm saying now we can use our power rule and my derivative function. So if we follow that pattern, where does that 2 go? Out in the front. So there's already a number there. So guess what we're going to do with those 2 numbers? 6, multiply them, and then it's going to be to the exponent of 1. That's your derivative function. Okay. Is that way faster than using the 2 formulas? Yes. Okay. And the constant multiple rule, that just is what I just did with you. If there's already a constant out in front, right, that stays, it gets multiplied by the exponent that you brought down. So if they were all that easy, it would be perfect. There's going to be some that we have to manipulate the original function, so for us to be able to use our power rule. Okay, so let's do a couple easy ones first. So this one, my derivative function, which again, remember guys, is just my slope function, is going to be what? Right, 15 x squared. Done. So our calculus rules, guys, makes it so much more efficient. Okay. This little guy here, right, will be negative 12x to the what? Ah. Okay. So negative 4, and then what are we going to do? Right, we cannot leave, that's one of our rules, guys. You will never leave negative exponents, okay, in any of your answers. So then you would do one quick more step. So negative 12 is fine, but that'll be all over x to the power of 4. And that would be your derivative function. So with this little guy here, do we have to do a little bit of manipulation before we can do the question? Yes. So we need to get rid of that square root. So I'm not doing anything crazy yet. I'm not applying any derivatives. I'm just going to change this to x to the power of, perfect, 3 over 2. Now it's in the form that we can use our power rule. So now my derivative function. So we can, remember notation, guys? What will I have to put on the y now? Y prime, right? And you could technically, if you like this notation better, I'm going to rewrite that, but remember you could write dy, what do I have to put on the bottom with this one? Dx, because it is in terms of x. Right, if this was a g equaled 4 and then the variable was an a, right, then you would have to use those variables. So this, right, or this would be perfect notation to say that you're doing the derivative function now. So this one, since it looks a little scary, I'm just going to show the work. Does the 3 over 2 have to come down? So we are going to go negative 4 times 3 over 2, which will just be negative 6. And then x, 3 over 2, we are going to have to subtract 1. So again, you guys wouldn't have to show this work. So I'm left with negative 6x, and that's going to be all to the power of 1 over 2, because 1 is 2 over 2, so 3 minus 2 is 1 over 2, which is half. That is acceptable, so I would accept this answer. Whoopsie. Would both those be the same thing? Probably in an answer key, they'd probably write it back to root x, but like I said, either one of those I would mark correct. One's not more simplified. I prefer the root x just because that you can see the restrictions on x a little bit faster. Not that I want you to give those to me right now, but that would be it. All right, so with this one, do we have a problem? Yes. So right now we cannot use the power rule because what operation do you see in the question? Division. So you could use the quotient rule, but that would make it really complicated, and you don't know the quotient rule yet. So you have to manipulate that because you only have the skills right now to do power rule. So I got to move that up to the top. So that would be the first thing you'd have to do. And the thing is, even once you learn the quotient rule, guys, you're still going to want to do this, right? Quotient rule is much more complicated. You always want to make the question least complicated. So your power rule is the least complicated rule. So if you can ever manipulate the original, that's equivalent. So you can use the power rule. That's what you're going to want to do. All right. So now we're good to go. So then we're going to get our derivative function, right, would be negative what? Good. Negative 8x all to the power of? Perfect. Which is the same as, perfect, negative 8, x to the 5. And you're done. Okay, so a few more that I want to do with you just to show you guys that sometimes you have to do a little bit of work before you can apply it. So again, with this one, do you guys need to simplify that? Yeah, because as of right now, it's in quotient rule form, but you have the ability to change this, so that's what we'll do. So let's fix this. This is going to be the same as f of x equals 3x to the power of what? 9. Good. Because it's either two ways to look at this. You can use your exponent rules from grade 10 and go 7 minus a minus 2, which is 9, or can I just move the x to the negative 2 up to the top, right? And then you're adding your exponents. So either way, I don't care. Way to look at it. So then now we have our derivative function is going to be 27x to the 8. And you're done. Okay. Second last one. So again, technically, guys, what's operations happening in the y function right now? where operation is happening with these two terms. Multiplication, okay? So it's multiplication, so we cannot use our power rule right now. We'd have to use our product rule, which we don't know yet. So therefore, you are going to have to simplify this so it's one term. And you guys have the skills to do that. Right, so this is going to be the same as x times x to the power of what? Right, 1 over 3. Oh, you thought the 3 was on the x? Yeah, no, it actually sort of looks like that, doesn't it? So next time if I give you one of these, I will separate them a little bit, because did anybody else think it was x to the power 3? Right? So again, I understand why you would have. So yeah, it is, I apologize. It's not original, just as you walk around the school. All right, so I apologize, it did look like that. So it is the cube root of x. So then now what do we do to our exponents? Right, so that's 3 over 3 plus 1 over 3, which is x to the power of 4 over 3. Now we can find the derivative. Right, so our derivative function, 4 over 3 comes down. And then we have x, and then remember we're going 4 over 3 minus 1, but minus 1 in this situation will be a 3 over 3. So that's going to give you a 1 over 3. And so then you could leave it like that. That would be acceptable. So I don't mind you guys leaving fractional exponents, so I'd accept that answer. Or you can change it back to root form. Right, so then this would be the same thing as cube root x. You should understand, like even though I'm saying you guys can stop with leaving as a fractional exponent, you definitely should understand how to change back and forth though. Because with answer keys and stuff, usually, like I said, they will go to the root form. All right, last one, and then I'll let you guys have some time to work, and then we'll do lesson 3 as well. So here it just says find the equation of the tangent line to the curve y equals 2x cubed at point 2, 16. So in chapter 1, this was a little bit time consuming. In chapter 2, very quick. So what's my derivative function? Right, 6x squared. So remember, that derivative function is still my slope function. So can I use that now to find my slope? Pardon me? So remember, is this my slope function? So I can change that y prime to m. Because is it my slope function? Yes, so since it's my slope function, it's also my m equals function, which m is standing for slope. So what do I put in to get my slope? Just my x value. So if I put my x value in, I'm left with 24. So there's my slope. And now I have my point because I'm missing my b. Right, so we wrote lots of equations of lines. It's just getting our slope function was a lot more lines in chapter 1. So now we have y equals mx plus b. So y is 16, my slope's 24, my x is 2. So then we have 48 plus b. So b is going to equal negative, not 4, negative 32. Now we have everything we need. Because you need to see where it came from. But now you guys can appreciate this. Don't you guys appreciate it now? And are like much happier. So 24x minus 32. Right, so the nice thing is, guys, we're still just building on everything that we've done so far, right? We haven't done a lot, but we're just now making it more efficient, okay? Yeah.
This is kind of one question about like what they really are. So when we're finding the derivative, that's saying that whatever point on our original function we want to find the slope of the tangent line, we just put that line in for x. And so that, okay.
Right, so our derivative function is just our, like if we have to apply something to it now, it's exactly that. What can our derivative function do for us? Just in context of what we've done so far, it will give us our slope of a point of tangency. The other thing it could give us is because our first derivative is also velocity, right? So this is our velocity function, right? Because did we do a little bit of velocity in chapter 1? Yes. So this also, right? So what this little guy does for us, right? So that equation right there gives us our slope at points of tangents, okay, our tangent points. It also could give us velocity at x equals if it's a time of 2 seconds, right? So it's our velocity function, which again, we haven't did any velocity questions here in chapter 2 yet, but does that make sense though, guys? It's also our velocity function, okay? So it does give us slope at tangents, and it also will give us velocity, is what we can do with this first derivative function. Okay. All right, so I just want to give you probably 15 minutes-ish to go to your assignment booklet, do some practice, making sure, I'm not worried obviously about these tally questions. Should those ones be done in your sleep? Yeah, so I would now pick a few questions where you actually have to do a tiny bit of work to clean it up. So C, D, E, F, so go to the assignment booklet, pick some of those, do a slope question, and that should be enough practice for this lesson. And then we'll do the next lesson, like I said, in 15-ish minutes.